Everyone. So in this video, we're going to continue with the Ford F-150 problem. So far, just to recap, the dealer said that the mean price is $18,800. We collected a random sample of 14 vehicles, which is a small sample. So we can't use our norm.dist function. Instead, we have to find something called a t-value and use a t-distribution to find the probability. In this case, since it was a two-tailed test, we had to multiply by 2 to get the true probability, which was still less than our level of significance. And this is also a good time to point out that if we were looking for something, let's say that the mean price of the 14 vehicles we came up with was $19,000 or $20,000, something that was greater than the mean that was claimed by the dealer, we would then do a 1 minus the t-distribution because it's always giving us the area less than, or the probability less than the value that we're giving them. And so if we're looking for the probability outside an upper tailed test, we would do 1 minus the distribution given, or the probability given, so that we could get the true probability of the right tail. So then, since the p-value doubled was less than the alpha value, we rejected the null hypothesis, which means that the average price of a Ford F-150 is not $18,800, which could result in a type 1 error, meaning it actually was $18,800 and we said it wasn't. So now we want to find a confidence interval for this same problem. And so for the mean that we got was 18,000 and a standard deviation of 1250. Previously, what we would do if this were a large sample size, greater than 30, we would just use our norm.inverse function and use the probability, the confidence probability to find the lower bound and the upper bound because we know we're splitting the 5%. So we'd put 0.025 for the lower bound, we'd put 0.975 for the upper bound, and we'd find those two values. So this is similar, except we have to do an extra step because it's not going to take the mean and standard deviation and just spit out the value for us. Instead, it's going to give us the t-score, and we're going to have to multiply that by our standard error to figure out how far from the mean are we actually going to be. And then we subtract that margin of error from the mean, and we add the margin of error to the mean to find the lower and upper bounds. So let's go ahead and rewrite the information that we were given and that we need. So in this case, we know the mean x bar. This is our x bar. The mean was 18,000 for the sample that we found. We know that historically mu is 18,800, but I don't really care about that value. It's nowhere in this formula, and remember, when you're setting up a confidence interval, what you're doing is you're assuming that the mean of the sample that you drew out of the population is the true mean, and then you put you create an interval around that true mean, and you're hoping that the population mean is somewhere in that interval, and if you're doing a 95% confidence interval, 95% of the time that you do this task of pulling out a sample of 14 Ford F-150s and finding the mean price and creating a confidence interval around that, you should be capturing that true population mean 95% of the time. So we have our mean, we need our standard deviation. That was 1,250. We need our sample size. That was 14, right? 14? Yeah, 14. Okay, so let's go ahead and find the values that we're looking for. So first we want to find the critical value. And what this critical value is, it's the same thing that we put into our norm.inverse function, except now we're going to put it in something called the t.inverse function. So t.inverse, you put in the probability. So if this is a 95% confidence interval, that means there's 5% on the lower and upper sides. So we have to split that 5% into the two parts. So that means there's 0.025 on the bottom half. And the other thing we need to know is the degrees of freedom, which is the sample size minus 1. So if we do that, we get our t critical value, which is negative 2.16. That's this right here. So now I have to take that value. If I want to find E, I have to take that value, E being the margin of error. I'm going to take that critical t-score. I'm going to multiply it by the standard deviation, and I'm going to divide by the square root of 14. Now this gives me how far away am I from the mean. Okay? Now, we technically just want the z-score. So the upper z-score is going to be the same value. If we were going to do t dot inverse again, and we did the 0.975, which would be the upper end of this, and then 14 minus 1, we would get positive 2.1603. And technically, we want to use that positive value here. We don't want the margin of error to be negative because I'm going to subtract that value and I'm going to add that value. So we want the absolute value of this. So you might want to find the upper end. If we did exactly what we had before, we could always just take the absolute value of this number to get the 721. So this is saying that my confidence interval is going to include means that are $721.73 below the mean of the sample and above the mean of the sample. And so my lower bound is going to be the mean minus this margin of error. My upper bound is going to be the mean plus this margin of error. And this is my confidence interval. Now, I rejected the null hypothesis. Is the null hypothesis mean in this interval between $17,278.27 and $18,721.73? The answer is no. This mean, 18,800, is not within my confidence interval. And I should only miss the mean 5% of the time. And so this is why, this backs up my claim that we should have rejected the null hypothesis, because it doesn't seem like normally the null hypothesis wouldn't be included in the confidence interval. But in this case, it's not. And so we're going to reject that null hypothesis. So that's the confidence interval part, and this would be what your answer looks like. It'd be, you can add a comma here if you really wanted to, comma, and these calculations to make it look more like an interval, whatever you want to do. Now let's go on to a problem where we are actually given the original data that was collected instead of just given the mean of that data and the standard deviation of that data. So for your study on the food consumption habits of teenage males, you randomly select 20 teenage males and ask each one how many 12 ounces servings of soda that he drinks each day. The results are listed below. At a 0.05 significance level, is there enough evidence to support the claim that teenage males drink fewer than three 12-ounce servings of soda per day? So each of these is the amount of servings of 12 ounces of soda that each male drink each day. You can see some are higher, some are lower, but they were randomly selected. So the only extra step in this problem would be that first we have to find the mean and the standard deviation. We have to find x bar, and we have to find my standard deviation. So x bar is the average formula. So I'm going to find the average of these 20 numbers. So that's 2.785. So far, our claim is that teenage males drink fewer than 3 12-ounce servings of soda, and this is less than 3, so that's a good claim. Our standard deviation for this sample, so we're going to use stdev.s because it's a sample, is 0.823 about. Okay. Now we need to know for a 0.05 significance level, do we have enough evidence to support the claim that this number is statistically significantly lower than 3? So let's talk about how we go through that again. First, I have to calculate my t-score. So I also need to know the sample size. Now it says 20 teenagers, but I can also use my count function to count up all these values, and that is 20. We're going to set up our null hypothesis. So our null hypothesis is that mu is equal to 3. Our alternative hypothesis is that mu is less than 3. And that's 3 servings of 12 ounces of soda. So that part's a little bit confusing, but we really just care about the servings, the number of servings. So I need to find my t-score. So my t-score is found the same way that a z-score is found. Is we're going to take x bar, we're going to subtract it from the mean, which in this case is 3. We're going to divide by the standard deviation divided by the square root of the sample size. So that gives me a t-score of negative 1.16. So now I'm going to find the probability that x is less than 2.785. And if this probability is less than 0.05, that means it's probably not due to just the natural variation in sampling distributions. It's probably due to some other factor, and so we reject the null hypothesis. But if this comes out bigger, we fail to reject the null hypothesis. And so I can't use my norm.dist. I'm going to use my t.dist function. First I have to equal sign. t.dist. I'm going to put in this for my value, and then my degrees of freedom would be 20 minus 1, and then cumulative is true. And so the value of 0.13 is greater than 0.05, and so we are going to fail to reject the null hypothesis, which means in the context of this problem that the difference in our sample mean is due to natural variability in the data. All right, so now we want to create a 90% confidence interval for these data. Now normally our confidence interval corresponds with our level of significance, and so a 95% confidence level would correspond to a 0.05 level of significance. So now I want to see if we're 90% confident, so if we're less confident, we can actually have a narrower confidence interval. I'm wondering if we would no longer contain the mean in our sample if we did it that way. And so what I need to do first is I need to find the critical t value. Now this is a one-tailed hypothesis test, and so we technically just need the upper bound of our confidence interval. And so I can use my t dot inverse function. And for a 90% confidence interval, there's 10% that's split, 5 on the upper half and 5 on the lower half. And so I'm going to put in an area of 0.95, and my degrees of freedom, again, 20 minus 1, and that gives me a 1.729 critical t-score. So I'm going to take that critical t-score, and I'm going to multiply it by the standard deviation divided by the square root of my sample size, and that should give me my value from the mean. So this is my E value. So this is my margin of error right here. And so my upper bound, which is really the only one that I need, is going to be the mean plus this value, which brings me to 3.105, and I'm still containing 3 in this confidence interval. And so I would have to seriously lower my confidence to capture. This does still capture the mean. So the question is, does this still capture the mean? And the answer is yes. And so this would be why I would fail to reject the null hypothesis, because the mean that's the historical mean of 3 servings per day, 3 12-ounce servings a day, is still contained within my confidence interval. Okay? So to interpret this result, the historical mean, mu naught, is still within my confidence interval at 90%, which confirms that we should have failed to reject the null hypothesis. What's the only type of error that could have occurred here? In this case, type 2. In the context of this problem, teenage males actually do drink less than 3 servings of 12 ounces of soda per day, and we are saying that they don't. Again, no one's getting hurt here, except maybe the person who's like, no, I don't drink that much soda. Yeah, I don't know who's getting hurt by this. So again, we've done our t-score. We knew that we had to do with t values because we only had 20 teenage males. Our sample size was given this time, so we had to calculate x bar and the standard deviation. But then the rest of the procedure is exactly the same as it has been for the last 3 classes. So hypothesis testing is exactly the same. How we calculate our p-value, that's the thing that's changing. We have to find the t-distribution, and then there's this t-score. All right, I'll see you in the next one.